In December 2025, astronomers and scientists across the globe will be watching closely as a newly detected object passes through our solar system. This object, referred to as 3I Atlas, has captured the attention of the international scientific community because it is not an ordinary comet or asteroid. Instead, it has been classified as an interstellar object, meaning it does not originate from within our solar system. Its approach represents the third confirmed case of such an object entering our neighborhood in space. The first interstellar object observed by humanity was Oumuamua in 2017. It was a cigar-shaped body that moved through the solar system before telescopes had the chance to fully study it. Its unusual shape and unexpected acceleration after its closest approach to the Sun raised questions that remain open even now. The second object, 2I Borisov, was discovered in 2019. Unlike Oumuamua, Borisov looked more like a conventional comet, although with chemical properties that stood out from the comets known within our solar system. With the discovery of Atlas in 2025, we now have another opportunity to study material from beyond our solar neighborhood. The initial detection of Atlas came from a survey telescope located in Chile on the night of July 1, 2025. The telescope is part of an ongoing project designed to monitor the skies for potentially hazardous asteroids. At 2:14 Universal Time, the system flagged a faint source of light. To most observers, it would have been imperceptible, but to the sensitive detectors on the telescope, it appeared as a point of light with a brightness of about 19th magnitude. For context, the magnitude scale in astronomy is somewhat counterintuitive. Brighter objects have lower numbers. The brightest stars visible to the naked eye may have magnitudes close to 1, or even negative values. In contrast, a 19th magnitude object is thousands of times dimmer than the faintest star the human eye can detect without assistance. In practical terms, this meant Atlas was extremely faint and required powerful instruments even to be detected in the first place. Within 24 hours of its discovery, the Minor Planet Center, which is the official body responsible for collecting observational data on small bodies in the solar system, issued a notice to astronomers worldwide. The analysis of its orbit showed that Atlas was not following the elliptical path typical of comets and asteroids that belong to the Sun's gravitational family. Instead, its orbit was hyperbolic, which indicates it is not bound to the Sun at all. Hyperbolic orbits are paths that allow an object to pass through the solar system once and then continue back out into interstellar space. This characteristic is what confirmed Atlas as an interstellar traveler. What made Atlas even more remarkable was its size. Observations suggested that it was tens of kilometers across. To put this in perspective, it is comparable in scale to Manhattan Island in New York. This makes it significantly larger than Oumuamua and Borisov, which were both smaller bodies. The size alone gives researchers a much better chance of gathering detailed data before it disappears back into interstellar space. Another striking feature of Atlas is its velocity. It has been measured moving at about 58 kilometers per second, or around 130,000 miles per hour. For comparison, Voyager 1, the spacecraft that holds the record for being the fastest human-made object in space, is currently traveling at about 17 kilometers per second after decades of continuous motion since its launch in 1977. Atlas is therefore traveling at more than 3 times the speed of Voyager 1. This is an extraordinary velocity, and it has prompted scientists to look closely at how such an object could have acquired it. In many cases, objects achieve high speeds through a process known as gravitational slingshotting. When a smaller body passes near a massive star or a planet, the gravitational pull can change the object's trajectory and accelerate it to higher velocities. This is the same principle used by mission planners to boost spacecraft towards the outer planets of the solar system without using excessive amounts of fuel. However, when astronomers attempted to trace Atlas's path backward through the galaxy, they could not identify any nearby massive stars, binary systems, or dense stellar environments, that could explain its observed velocity. This has left the origin of its speed unresolved, raising the possibility that the forces which propelled it are different from what is commonly expected. At this stage, global attention turned to telescopes capable of gathering more precise data. The James Webb Space Telescope, which orbits beyond Earth's atmosphere and has the most powerful infrared instruments available, was directed to study Atlas in detail. Ground-based telescopes, from observatories in Hawaii to facilities in Europe and Asia, also shifted focus to track the object. Even radio telescopes, which are usually tuned to sources such as pulsars or distant quasars, began pointing towards Atlas to see whether any signals or unusual emissions could be detected. This rapid coordination reflected the importance of the opportunity. A large interstellar object moving through the solar system is extremely rare, and the data gathered in real time cannot be replaced once it leaves. Spectroscopic studies, which involve splitting light into its component wavelengths to determine chemical composition, revealed that Atlas differed significantly from comets found within our solar system. Typically, comets here are often described as dirty snowballs, made up of about half water ice, along with dust and other frozen gases. Atlas, however, showed a strikingly low water content. Measurements indicated less than 5% water ice. Instead, its coma, the glowing cloud surrounding it, was dominated by carbon dioxide. This alone marked it as unusual. Further investigation revealed even more surprising details. The ratios of stable carbon isotopes in Atlas did not match the ratios observed in our solar system. On Earth and throughout the solar system, carbon exists in the form of carbon-12 and carbon-13, with a well-documented ratio of around 1 to 89. Atlas displayed nearly double that expected ratio. Isotopic ratios act like markers of origin, revealing details about the environment where an object formed, such as the conditions in its parent star system or molecular cloud. The results implied that Atlas was formed in an environment significantly different from the one that shaped the planets and smaller bodies in our own solar system. While these findings were already notable, perhaps the most surprising aspect of Atlas's behavior was its acceleration. Observations indicated that its path was not simply a stable hyperbolic trajectory. Instead, it was experiencing a small but measurable increase in speed. Normally, such acceleration is seen in comets when jets of gas and dust are expelled as their frozen materials sublimate under solar heating. These jets act like miniature thrusters, nudging the comet along slightly faster than predicted by gravity alone. In Atlas's case, however, the small amount of water and the weak carbon dioxide jets detected could not account for the level of acceleration observed. This unexplained acceleration has become a central puzzle for researchers studying Atlas. Unlike Oumuamua, which also showed signs of acceleration but was too faint and too small to study in detail, Atlas is large enough and bright enough to provide much more comprehensive data. Yet the basic question remains unresolved: what is driving its motion? For scientists, the appearance of Atlas offers an invaluable opportunity to study material and processes beyond our solar system. It also highlights the challenges of interpreting data from rare interstellar visitors. While Atlas will not come close enough to Earth to pose any physical risk, its trajectory and characteristics raise fundamental questions about how planetary systems form, how material moves between stars, and what kinds of environments exist in the wider galaxy. Atlas, however, does not fit neatly into this pattern. Its water content is extremely low, with less than 5% detected in its composition. The carbon dioxide jets identified in its coma are too weak to produce the level of acceleration that has been measured. This mismatch has led researchers to consider alternative explanations, though caution is always applied in such situations. In science, extraordinary claims require strong supporting evidence, and natural processes must be thoroughly examined before other possibilities are entertained. One hypothesis raised in the academic community relates to the idea of light pressure. Photons, the particles of light emitted by the sun, carry momentum. When they strike a surface, even though the effect is extremely small, they impart a force over large areas or very thin surfaces. This radiation pressure can produce measurable acceleration. Engineers on Earth have experimented with this concept through the development of solar sails, which are extremely thin reflective sheets that can be pushed along by sunlight. While still in the experimental stage, small-scale tests such as the Japanese Icaros mission and the Planetary Society's light sail projects have demonstrated that light pressure can be harnessed for propulsion in space. Some researchers, such as Harvard astronomer Avi Loeb, have suggested that the unexplained acceleration of interstellar objects like Oumuamua and now Atlas could be consistent with the behavior of light sails. If an object were a broad, thin sheet with low mass, the sun's radiation could accelerate it in a way that resembles the data observed. This idea has attracted attention because it provides a possible explanation where conventional models fall short. However, it is important to emphasize that no direct evidence currently proves that Atlas is an artificial construct or that it was engineered. The light sail idea is one hypothesis among several, and it remains speculative until stronger supporting data can be gathered. Whether natural or artificial, Atlas represents an important case study in how different planetary systems might form. The unusual isotopic ratios identified in its carbon content suggest that it originated in a region with chemical conditions very different from those of our own solar system. This provides insight into the diversity of planetary nurseries across the galaxy. Just as meteorites found on Earth give scientists clues about the early solar system, interstellar objects provide information about star systems far beyond our reach. The difference is that these objects do not require us to travel to other stars. Instead, they arrive here, giving us a brief window to learn from them. If Atlas proves to be entirely natural, its value lies in showing that planetary systems can produce bodies with unusual chemistries, compositions, and trajectories. This would imply that the galaxy is more diverse than models based only on our solar system might suggest. It would also challenge assumptions about how common or rare particular chemical environments are. For example, if high carbon-13 ratios are found to be typical in some regions, it may indicate the presence of processes or stellar events that differ from what shaped our own planetary neighborhood. If, on the other hand, Atlas were ever shown to be artificial in origin, the implications would be profound. Humanity is often described using the Kardashev scale, which measures civilizations by the amount of energy they can harness. At present, humans are not even classified as a full Type I civilization, since our species does not yet control all the energy resources available on Earth. A Type II civilization would control the energy output of its star, while a Type III would harness energy on the scale of its entire galaxy. A Type IV, still theoretical, would operate on a universal scale. In this context, an interstellar probe or engineered object would indicate a level of technology far beyond our current capabilities. Even the ability to build a durable structure capable of crossing interstellar distances would imply advances in energy, materials, science, and navigation that exceed anything currently possible for us. However, scientists are careful not to leap to such conclusions without conclusive evidence. The artificial hypothesis remains one possibility among many, and natural explanations must always be considered first. Regardless of its origin, the most immediate challenge with Atlas is time. Interstellar objects pass through the solar system quickly, and the window for detailed study is brief. Atlas was detected in July 2025, and by mid-December, it will make its closest approach before fading into the distance. Observers have estimated that the most useful data can be collected within a matter of days, after which its brightness will decline beyond the capabilities of even the largest telescopes.
High-resolution spectroscopy, imaging, and precise measurements of its trajectory must be carried out rapidly before the opportunity is lost. This urgency has united scientists and institutions across the world. Observatories have adjusted their schedules, competing research projects have been postponed, and instruments both in space and on the ground have been redirected. For many researchers, this collaboration highlights one of the strengths of scientific inquiry: the ability to respond collectively when a rare and significant event occurs. The fact that Atlas is not a threat to Earth allows this cooperation to focus purely on learning and discovery rather than on defense or hazard mitigation. The data already gathered may reshape our understanding of planetary formation, interstellar travel, and the chemical diversity of the galaxy. Even if Atlas is found to be entirely natural, its unusual features challenge the assumption that our solar system is a typical model for planetary science. It may instead represent one possibility among many, with other systems producing objects under conditions that we have not yet imagined. The discovery of such diversity is itself significant because it widens the range of environments where planets and potentially life could arise. For the public, discoveries like Atlas serve as reminders that astronomy is not only about distant galaxies or abstract theories. Objects like this bring the wider cosmos directly into our solar system, creating a rare moment when the unknown becomes close enough to study in detail. The fact that it will not return means that scientists must work quickly, but it also adds to the sense that this is a unique opportunity. In practical terms, Atlas will pass through near the orbit of Venus before departing into deep space. It poses no collision risk to Earth or any other planet in our solar system. Its importance lies not in danger but in knowledge. Each new measurement provides clues about where it came from, what it is made of, and how it behaves. In the years to come, the data collected may continue to be analyzed and reinterpreted, offering insights long after Atlas itself has vanished from sight. Events like this underline the importance of investing in large-scale telescopes and survey programs. Without the survey telescope in Chile, Atlas might have passed by unnoticed. Without international coordination, the opportunity to study it in detail would be lost. As technology advances, future surveys are expected to detect more interstellar objects, perhaps even smaller ones that pass more frequently. This means that Atlas may not be the last such discovery, but it is among the most significant to date because of its size and the timing of its detection. In summary, Atlas presents both a challenge and an opportunity. Its faint light carries information about chemistry and physics from beyond our solar system. Its unusual isotopic ratios, low water content, and unexplained acceleration provide puzzles that will occupy scientists for years to come. Its trajectory reminds us that our solar system is not isolated, but part of a larger galactic environment where material can travel vast distances. The answers to the questions raised by Atlas are not yet known, and some may never be fully resolved. But the effort to investigate it demonstrates the best of science: careful observation, collaboration, and the willingness to question assumptions when faced with new evidence. Whether natural or something else, Atlas highlights how much remains to be discovered in the universe. For now, it is a visitor passing briefly through our part of the galaxy, leaving behind data that may change how we understand our place in the cosmos. Humanity's task is to gather as much information as possible before the opportunity slips away, knowing that events like this are rare but invaluable reminders of the vastness and complexity of the universe beyond our solar system.